right, hi everybody. How are you doing? Thanks very much for coming out. This is the first time I've done something quite like this, so I'm a little jittery. I'll get it out of me though. Thank you again for coming, and this is Climate Change in Northwest Arkansas. And before I more formally and completely introduce myself, I just want to establish two important points for this whole conversation. And the first one is that while climate change is a big controversial topic, it's very divisive, there's lots of skepticism, there's lots of denial, and all sorts of responses out there. The actual science of it, the actual mechanics of how climate change happens is actually very straightforward and not controversial. You might have seen this little clipping on the left side here. It's gone kind of viral, I suppose you might say, on Twitter and Facebook and things like that. And it's a clipping from a newspaper in New Zealand in the year 1912, 111 years ago. And you don't have to read the whole thing. You can if you want. But what it's basically saying is that we are burning billions of tons of coal that releases billions of tons of carbon dioxide, and that makes the world warmer. It's just straight to the point and blunt and clear and totally straightforward and uncontroversial. This is 111 years ago, and it's actually a reprint from an earlier edition of the magazine Popular Mechanics. That's where this text comes from. But while I was putting this all together, I found you could actually go back even further. The clip on the right is from a science article by a man named Arrhenius, whose name you might recognize from high school chemistry. This paper is talking about what he called carbonic acid, which is kind of the term at the time for carbon dioxide in the atmosphere. And you can see he actually, there in the middle, he says, "The atmosphere acts like the glass of a hothouse or a greenhouse." So we almost have the phrase, the greenhouse effect, in 1896. So all of this has been really very clearly established, and I'll go in a little bit into the actual mechanics and the physics of that, not too deep, just a little bit in a few minutes, but I want to establish that. And then the second point that I want to make clear is that when we're talking about climate change, we're not talking about a single event, even if it's the craziest event you've ever heard of, the craziest headline. Weather gets wacky, odd things happen, extreme weather happens every now and then. I actually had a meteorologist that I talked to for a news article once who said that it's something to the effect of, it's not normal to be normal. You know, weather can be strange, and for weather to be perfectly average and typical and expected, that would be kind of odd and unusual. So it's not just one thing that proves climate change any more than a single snowstorm disproves climate change. No, it has to be patterns over years and decades and centuries. That's what we're talking about when we talk about climate, and also how the climate is changing. It's an accumulating pattern. It's a direction that things seem to be shifting. And I just wanted to illustrate that point. These articles are from kind of the last 10 years from all over the world of things that, taken together in a larger context, show us what's going on with the climate. So I just want to establish those 2 points. And then, so this is our agenda, and I'll start finally with saying who the heck I am and why you all are here. So my name is Dan Holtmeyer. Most of my career I've been a journalist or a writer of one type or another. Several years actually here in Northwest Arkansas for the newspaper, but also other states around the Midwest for about 13 years. And through that time I've been writing and reading a lot about environmental issues like climate and energy and invasive species, kind of all these sorts of environmental topics. That's been something that I have always gone back to. And so I started studying it and trying to learn about it even way before then. So about half my life I've been trying to get familiar with these topics. Just earlier this year I finished my master's degree at the university in geography with a particular focus on climate change, and also what they call green infrastructure, which, if you're not familiar with it, is essentially living infrastructure, kind of the unpaved spaces, parks, streams, natural areas, how they are arranged with every other type of infrastructure, roads and houses and everything, and all of the services and benefits that they provide to us, which are many, as you can probably imagine. And then within the past year, I've begun to start a new native plant nursery called Ozark Roots, which I'll talk about a little bit later. But the idea of it is to focus on plants that are native to the Ozark region, the Ozark Plateau that goes up into Missouri, and also with an eye on preparing for what is on the way, for the climate change that's expected to come here, and what we have to get ready for, essentially. So plants that have adaptations that are helpful for that. That's the whole focus of it. So that's me. I want to give a shout out to this whole event is actually made possible by an idea accelerator or a business incubator called Builders and Backers, which you might not have heard of, but it's connected to the Heartland Foundation, which is just up the road in Bentonville. So they've been a big help for getting all this rolling. And then in the back is Nice NWA, which I sure appreciate. They're recording all this for posterity and for anyone who couldn't make it tonight, because there are a few who wanted to. Okay, and so for tonight, we'll be looking at, I'm going to give you a sort of a crash course on climate and climate change, kind of just the real fundamentals of how it works and what's going on these days. And then we'll move on to what we've seen so far, kind of climate change to this point, and also looking into where it's going into the future. We'll get to the effects that all that might have on just kind of just a little cross section of plant species. I can't give you a comprehensive look at the several hundred native plant species that we have around here, but I'll give kind of a sampling, and that should give an idea of what plants are going to be dealing with and how they could react to that. And then I'll end with just a very short spiel about Ozark Roots, but I also want to draw your attention to the other native growers in the area. There are several others that are up and running, selling plants right now, even just today. And we're all on the same team, so I want to tell you all about them. Okay, so I'll start with a definition of climate, what we're talking about. What you'll find, the typical definition of climate is something along the lines of the study of the weather and the atmosphere over time, maybe in a certain spot, but that's the real basics of it. But if I may be so bold, I want to kind of give my own spin on that definition, that climate is the flow of energy and water on the planet. And that's a really big, vague, wide-reaching definition, because climate is big and wide-reaching. It touches on geology, landforms. Mountains and plains affect the climate. They steer wind, they block rain from certain areas, things like that. But climate also turns around and affects geology. Erodes those same mountains and makes a difference on what those landforms are. It's affected by the oceans and the flow of heat through the oceans, but it also affects the oceans. It affects life. Obviously, all living things depend on the temperature and the moisture available in a certain place. But life itself also affects the climate. We as a species are really proving that, but even throughout history, all sorts of living things have made a huge difference on what the climate is doing. And so I wanted to just give this big definition. It's the warmth, it's the coldness, it's the wetness, it's the dryness, it's how they collide with each other and oppose each other, it's how they flow into one another and turn into each other, and how that moves around the surface of the planet. And when we're talking about energy, for the most part what I'm talking about is energy that lands here from the sun. It comes to Earth and gets through the atmosphere the crucial part here is that it's absorbed by the ground, by the water, by the clouds, by the air itself. It's absorbed and then it's re-emitted, and it's re-emitted as heat. And you can actually feel that heat for yourself. After a hot summer day in the evening, you can feel that heat coming off of the sidewalk or coming off of a brick wall. That is going on a global scale, that heat. And crucially, when we talk about greenhouse gases like carbon dioxide or water vapor, they let sunlight come through, but they are much better at blocking and holding on to that heat. That switch from sunlight to heat is where the greenhouse effect comes from. So that's and once it is absorbed and re-emitted, it's kind of like a stock market, and that's just what this diagram is to show, that there's just a bunch of buying and selling, kind of trading back and forth of that energy. So the ground absorbs some energy, and then it gives it to the sky, to the clouds, and then the clouds give it back to the ground, and then some of it goes out into space, and it's just like everyone, it's trading hands over and over and over. And what that means is that it's kept, it's held onto, it's kind of slowed down, because energy will go back out into space and be lost. But in the meantime, it's changing hands so much that it sticks around for a little while. And thank goodness for that happening, for that slowing down and holding on to that energy, because what it does is kind of establish what you might call a savings account of energy, so that when the sun goes down and we are not getting blasted with more and more energy, all of that energy doesn't just immediately disappear into space. We actually hold on to it. Because if it didn't, we would have a very, very different kind of situation on here, and we only need to look at our closest neighbor, the moon, which gets the same exact sunlight that we do. But in the daytime, you'll get up to about 200 degrees, and then in the night, when in the shadow, when the sun isn't providing any more energy, it escapes immediately, and you'll get down to negative 200 degrees. So thank God for the greenhouse effect. I will say that, and you can quote me on it. But what we've done over the last century and a half or so is we've really supercharged that whole process by adding a whole lot of carbon dioxide to the atmosphere, by burning coal, burning gas, burning oil, burning natural gas, all these fossil fuels. It comes to tens of billions of tons of carbon dioxide a year, which is a huge number, but also kind of a meaningless number. It's hard to wrap your mind around that. And so something that gives a better sense of that is actually this excerpt from a really interesting story. It was 4 years ago in the Atlantic by Peter Brannon, and at the time he was writing about the terrible wildfires that were going through the Amazon. And there was kind of this odd little hysteria about, if the whole Amazon burns down, then we're going to be out of oxygen. We can't breathe. They're the lungs of the planet. And the burning of the Amazon is very, very bad, but it is not that bad. Just to put that out there, all the oxygen wouldn't disappear. But what's pertinent to this whole discussion is he dug into the actual absorption of carbon and what that actually means. So we think about plants and trees as absorbing carbon, locking it away and holding onto it. And that's true while those plants are alive. But once they die and they burn or they decompose, a lot of that carbon is just re-released. It might not be a perfect one-to-one, but there is a balance of carbon, the carbon absorbed and then carbon released by the decomposition and the digestion of those plant materials. What was remarkable or kind of amazing about the formation of fossil fuels a couple 100 million years ago is that happened because the carbon was locked away. It didn't get re-released. There were so many plants growing at the time, and this was so long ago that decomposition, as we think of it now, basically hadn't been invented yet. So there was a ton of carbon, and it was being buried, and it was being kept there, it wasn't released, and it was locked away underground and buried for millions and millions of years, and that's where we get our fossil fuels today. And so what we've done is we've essentially unsealed the tomb for all of that carbon. We've brought it back out, and we've burned it to get it back into the atmosphere. And this image will always just stick with me. It is a forest fire of the eons. It's not just forests that exist right now that might be burning. We are burning forests that haven't existed for millions of years, that have been gone. We have brought them back, and we're burning them too. It's a forest fire for the eons of the ages, essentially. So that image has just always really stuck with me. What difference that has made, what climate change actually kind of boils down to, there's a whole lot of nuance and detail, of course, and variation depending on which part of the world you're talking about. But a lot of what climate change has meant boils down to these 2 points, and they are related to each other. First is that temperatures on average are going up. And that's the whole global warming phrase. That's where that comes from. Temperatures have been rising. I think the global average is about 2 degrees Fahrenheit over the last century or so, which might not sound like a lot. But when you think about every hour or every night being 2 degrees warmer than it would have been, every day being 2 degrees warmer than it would have been, every year being 2 degrees on average warmer than it would have been, that is a lot of energy. That's a lot of energy over a state, over a continent, over a planet. That is a lot of extra energy flying around. What's interesting about that is that the destination of a lot of that warming is the cold, at cold places and cold times. And what I mean by that is cold times of year. Winter has warmed up more than summer around the world. Cold places, the Arctic and the Antarctic have warmed up more than here or the tropics, and that's why you hear a lot about sea ice vanishing and the permafrost thawing and things like that. Even down to the day, nighttime has warmed up more than daytime, and there's probably a lot of science behind that. But to put it real simply, it's at least one reason is that there's a given amount of sunlight. We're not going to get more sunlight in a day, and it's not like it's being magnified or anything like that. We get our sunlight, we get our daily delivery of energy, but then at night, when that energy might escape into space, it's being caught, it's being held onto more than it was before. So the nighttime is warming up more than the daytime. And then related to that, kind of the other big impact is that unusual weather, extreme events, becomes more likely. And they can be kind of paradoxically opposites. We can have droughts and wildfires, and we can also have floods and terrible storms, even in the same space, even in the same location. That can be happening. And there's lots of nuance and detail behind why that happens, but two real simple explanations are warmer air holds more moisture. It's able to absorb more water vapor and evaporate more. And so it can carry more water to you and dump it on you. And then it can also take more water away from you and take it away somewhere else. But also beyond that, heat and the transfer of energy is what weather runs on. It's the fuel for storms, and there's just more juice for them to use when temperatures are going up. I have some maps and graphs to just kind of illustrate all those points. So this is showing basically the temperature anomaly. I believe it was 2022. I think this is from NASA. Over the past century or so. And so you can see things kind of fall into the 1 or 2 degree range, and then you get to the poles and it's 4 or 5 degrees. So it's very concentrated up there. For the US, over the last century or so, it's more or less the same picture, a couple degrees warming. You'll notice with Arkansas and some of the nearby states, there's some gray there, and even some light blue, which means a little bit of cooling. They call this the warming hole, which is quite a name. Scientists have a knack for names, definitely. And there is still research into why this is going on. There's a couple ideas. It could be just sort of a fluke, from the kind of the permanent high pressure systems that are parked over the North Pacific and the North Atlantic, and maybe they just interact in a certain way that this happens. It could also be more rainfall that's coming to this part of the country, or even more irrigation for farming, which in effect acts kind of like sweat. It's just this water that's spread over the landscape, and then it evaporates and takes some heat with it, just like your sweat does to cool you off. And so that this might be the result of it. But I will add that there are some indications that us having it easy here with climate change compared to the rest of the country and much of the rest of the world could be coming to an end pretty soon. Actually, over the past couple decades, we've gained ground. We've gained a lot of ground to kind of get where everybody else is, and that's expected to continue. And then you can see here, just illustrating that point about the seasons and how much more warmth the winter is getting compared to other months. And this is for the lower 48 since about 1900. And you can see winter has warmed up about twice as much as summer and fall, and spring is in the middle. This is just illustrating the point about weather extremes. This is a again, for the whole U.S., heat wave frequency and how long they go on and how intense they are. And you can see there's pretty clearly a single direction that this is all going, and it doesn't seem to be slowing down. And then again, warm nights, and I want to come back to this. So this is just looking at the southeast, and you can see we're right on the very edge of this region in the National Climate Assessment that came out several years ago. And nights that don't get to 75 degrees or cooler have been on the rise, on pretty significant rise, especially over the last few decades. And this is really important for people, for plants, for other living things. If you can imagine, I mean, it's not hard to imagine because we had a couple of these last summer, a night that doesn't get colder than 80 degrees and how much that just wears you down and how miserable that can be. It can literally kill people. One of the big risks or hazards of climate change is heat deaths, and a lot of that is because of how hot it is at night, because you can't recover from a hot day and you can't prepare for the next one. And that's true for people, that's true for animals, that's true for plants as well. It's just sort of this accumulative stress that wears down your defenses, honestly. And then this is just for Arkansas, this graph. This is from NOAA. Looking at days with 3 inches of rain or more. So these are the real deluges, the real downpours, extreme precipitation events. And you can see for most of the last century or so, it's gone up and down a little bit, but it's held fairly steady with just your typical variation. And then over the last few years, there is an unusual spike. wait, before I get to that. So I wanted to get to the idea of how we know, like the weather changes, like I said, things happen, things shift through all of Earth's history. We've had ice ages, we've had kind of hot worlds where everything is tropical, we've had crazy things. So how do we know that it's because of us and because of what we have done? And the answer is not the matrix, but simulations, basically. Simulations of the weather over and over and over again. The term that you'll usually hear is models, climate models. And this is just from basically kind of taking the physics of weather, what happens when air temperature does this, what happens when humidity does this, what happens when the jet stream does this or that, and putting that into mathematical formulas that computers can solve. And the way that they do that is by dividing up the atmosphere and the Earth's surface into these building blocks. Or you might think of them as almost like 3D pixels of a model, where you solve, or a computer solves those equations, starting with certain weather conditions and weather measurements. What happens next? Solve that for that block and that block and that block. And you do that multiple times, and you do it for all the blocks, and you can get an idea of what the weather or climate should do. And the neat kind of thing of that is that you can test it. You can see how good a model is, and you can find out if it's worth using. And I wanted to pose the question to the group if anyone can think of how you can test a model like this. Any ideas?
Do a model for the past.
That's right. Excuse me. Yes, you see if it can predict things that have already happened. You plug in conditions from yesterday or a week ago or 100 years ago, whatever it is, 100,000 years ago. You plug in the measurements that the conditions, and you run it. And you run it multiple times, and you see if it kind of settles on basically something close to what happened. And you can test it out that way. And if it does a pretty good job kind of predicting what happened in the past, then you have something that's fairly useful, that's fairly usable. And what you can do, so that's useful for the present and looking at the past, because you can basically ask a model to pretend that we never came around and started releasing all these greenhouse gases. You can kind of subtract what we have thrown into the atmosphere and give it this pretend world and say what would have happened and without us doing this, without us making these changes and doing that and running the simulation, the model many times, and comparing it to what you know. So when you see or hear a headline about how a certain heat wave was 50% more likely, because of climate change, or a hurricane was 70% more likely to hit this spot because of climate change. That's what it's from. It's from those models and just the very basic percentage difference between the two. Sorry. So the models aren't only useful, obviously, for looking at the present or looking into the past, but they can project into the future, and that's where climate projections and climate predictions come from. For Northwest Arkansas, those projections are basically boiled down to the same two real principles that we saw for just the Earth itself, or the whole world: a steadily rising temperature, and again. That warming holes time is just about up, it looks like, and then really what you might think of as an intensification of the water cycle, an intensification of the weather, where it's not just a storm, it's a major storm, and it's not just the normal dry spell in between the storm, it's longer, or it's more intense, or it's both. Just really taking those normal ups and downs and juicing them up and making them bigger swerves. And on a website called KNMI Climate Explorer, you can actually run some climate models and see it for yourself for a specific part of the Earth. So I plugged in a couple latitudes and longitudes that basically make a box around Northwest Arkansas, and you can run the model through that website, and all the scribbles, all the crazy ups and downs are all of those model runs. So you run these models, multiple times to kind of see where they settle, where they tend to land. So that's what all the scribbling is. And then those thick solid lines are kind of where things seem to be most likely, where they keep ending up. And so you can see the black line is up to now, and then the blue line there is what you might call a very optimistic proposal. Like if we were suddenly really, really serious about all this and stopped using fossil fuels and moved to different kinds of energy, we might get a couple degrees rise still, but it levels off. It doesn't keep going and going and going. And so we'd be able to deal with that a little bit more easily than the non-optimistic scenario. If we just keep on doing what we're doing, and we keep on burning fossil fuels and even burning more of them because there's more of us, and just kind of going on the trajectory that we always have, you're talking about 4, 5, 6, 7, 8, 9, 10 degrees of warmth, and it's not slowing down. It just keeps on going by the end of the century. So that's right here, kind of in the Ozark area. And again, looking at those warmer nights in particular, so on the left side is kind of current conditions. And you can see we're this very light color where we just get a handful of 75 degree plus nights a year, like 5 or less even, on average. With the more optimistic scenario, that might turn into a couple of weeks a year, all added together, a couple of weeks of nights that warm. And with the less optimistic scenario, that could become several weeks or even months of the year where the night stays that hot. And again, that translates to people's health, doing worse, people dying. And so for plants, I just want to focus on kind of two main points that this boils down to for what this all means for the plants that live here. First, we have with warmer temperatures, we have more time that plants can grow. This study from about 15 years ago found that in temperate regions, which is kind of where we are, not tropical, not polar, but in the middle, spring has been, or bud break, which is when the leaves or the flowers start emerging, has been advancing in the year 1 to 3 days per decade, and that was 15 years ago. So I would be willing to bet that that's even faster now. And then the growing season overall, like from beginning to end in Arkansas, has gotten about 2 weeks longer over the last century or so. Let's see, yes. And then, so what, that changes the amount of heat stress that plants go through. It changes, there's changes to the water stress, how much water is pulled out of a plant by the heat and the conditions around it, how much water it needs to find to stay healthy. It affects all of those things. And the result is that the range that a plant is happy growing in, kind of its ideal areas where it can grow and thrive, changes. Sometimes it's a good thing at least as far as the plant is concerned. It gets more area to grow in, and it's loving it. It might love a certain species might love the conditions that are on the way. Others basically have to move, and they can move toward the north, like toward the poles, really, or they can move higher in elevation. But it's both for the same reason, kind of seeking out those normal temperatures, the temperatures that they used to have. They try to follow them. Like, no, I need to stay where it's relatively cool. There was you can see a lot of this in animals. One you might know is the armadillo, which has been around here for a while and has been spotted in Kansas and Missouri for a long time. But over the last couple decades, it's made its way as far enough as Nebraska and Iowa and Illinois. It's just kind of marching northward, the march of the armadillo. A lot of butterflies and bugs are pretty mobile, and so you can see that kind of shift really clearly with them. But even plants are obviously less mobile, so they have less motion in them to use. But there was a study of Southern California forests and the species in that, and over the last 3 decades or so, those species have moved upward about 65 meters. Just kind of at least the ideal range, kind of the concentration of where you would find that plant. And this can be a good thing. This movement can be a good thing. When conditions are changing, if it can be, for a plant, it can be, move or die, like move or go extinct. So being able to go upward in elevation or to move toward the poles could be what allows a plant species to continue. So that's a good thing. And that's why groups like the Northwest Arkansas Land Trust will try to preserve tracts of land that connect, that form what they call corridors, so that all sorts of living things, but including plants, so that they can move, that they have somewhere to go without colliding with highways or human society in general. They can actually make that shift as they need to. But movement also has its drawbacks and its issues. One big issue, or one big open question for a lot of plant species is can they keep up? Can they keep up with the amount of distance that they need to cover to find the kind of weather conditions that they're used to? A lot of plant seeds in a year might move a few feet, honestly, and even if they can catch a ride in a bird's stomach or something like that, who knows which direction the bird goes in, if they're going the right way for what the plant might need, and not every plant can count on that. And so the pace of that required movement. There's a few different estimates out there, and there's debate and disagreement. But an estimate that I saw was that that movement of temperature and conditions is about a mile northward a year, and about a yard upward a year. So it's a lot easier to go up than it is to go horizontally, toward the poles. And with a lot of plants, they might need some help. They might not be able to move at that speed without some outside assistance. Another issue is that the change in suitability, the change to the degree that a plant can deal with certain conditions is not, that change will not be the same for every plant species. And so you have, I think the term that they used was detachment. Plants that always have been around certain other plants and certain other animals form, I always think of it as a tapestry, as a fabric, a living fabric. And if one species has to go and another doesn't, then you start pulling apart that fabric, where those interactions, those ecological connections might start to fray. That's a big problem. And then in the destination where something might be moving to, you can get something kind of like an ecological pileup, where suddenly there's a whole bunch of newbies in town, new plants, new things that eat plants, new competitors. Just suddenly a whole bunch more to deal with for the plants that were there, kind of in the destination. So that can bring its own issues. Let's see. Oh, and then besides the plants that we're talking about, some bad things are also moving, like diseases and pathogens. So this isn't for Northwest Arkansas in particular, but for the American chestnut, which is mainly over, as far as it still exists, is mainly over in the Appalachian region. And there's a root disease called root rot, or it has some other names. And that disease is kind of held at bay by the cold. It doesn't really cross a certain latitude. And what is that latitude doing? It's moving. The barrier of cold that was holding back that disease is moving upward, and more chestnuts, which have been through enough over the last couple centuries, more chestnuts will become vulnerable, kind of in the sights of that disease. And then there's, like I said, with competition, and if a bug eats plants and it moves to a new area of plants that have never had to deal with it before, and suddenly it's just a buffet. All of these things can really add up and cause a whole lot of ecological problems. And so I'll exit out of this because this is just a neat illustration of it. You all, I'm sure a lot of you are familiar with the plant hardiness zones, kind of they really set the boundaries for how cold certain parts of the country will get. Oh gosh, if it loads, yeah, here we go. And so this is a present condition, and this tells you a lot about what plants will thrive in certain areas and how, based on how cold they can get and still survive. And you'll see, Northwest Arkansas is generally, I think, in 6B, or just zone 6, basically, which means you can expect a typical year to get down to about 0 degrees, and that's kind of where things fall. And they set those zones for the whole country. And then, so you see that map, and where this kind of darker green. And then as you look over the next century, this is what they expect hardiness zones to look like. So we could move up 1 or 2 zones, which is several degrees, which means that plants that need the cold have to leave, and plants that love the heat can come in, or can be a bigger presence. So I couldn't really put that in the slideshow. I just love that swipe, so I wanted to go to that. And this is just that same kind of deal, but focused on the southeast again, just to give a closer look, where we're in that nice light blue, and then over a non-optimistic scenario, we could get into zone 7, or even kind of reaching into 8. And so, with all that in mind, I wanted to now just run through a few kind of focus species. And I really love the white oak, so I wanted to start with this one. This is a really important hardwood, and it's very commercially important. It's basically from the Great Plains east. It's a very widespread tree, and it's a very flexible tree. It can deal with all sorts of different moisture levels and temperatures. It's a versatile tree. As you look at it. And this is pretty straightforward, not unexpected, but when summer temperatures rise, the tree grows more slowly, and when there's less water around, it grows more slowly. And even if what we're talking about with Northwest Arkansas, when you look at the whole year of total rainfall, that number might actually stay the same, but because it's more concentrated in these few more intense events, and there's longer stretches in between them, for a plant, it feels like there's less water around, there's less to depend on, or you can't count on it always being there. And so, this one study from a few years back speculated or projected that on the western edge of this plant's range, which is right where we are, kind of the western fringes of where it can grow, these trees could start to grow a lot more slowly, to kind of I don't know if struggle is quite the right word, but not be as boisterous, not thrive as much. And meanwhile, in the Appalachian side of its range, it could be doing great. It could actually really be having a good time. And so the population of it might kind of start to lean in this way, to be sort of lopsided, where it's not not doing quite as well over here and thriving over on the other end of things. And then there was another study from just a few years ago that its ideal habitat, this is not just anywhere that could eke out a living, but it's ideal conditions where it does the best and it's most adapted. That area could really sort of withdraw from the U.S. in a lot of ways and move up into Canada. And that last study that I was talking about actually looked at several tree species, and this is just the example that they illustrated. This is for sugar maples. And those flecks of red and magenta are where habitat would be lost. So sugar maples and also really probably some other maples, black cherry, and a few other species really might not like to be around here nearly as much, basically, and start to move toward Canada and toward the northeast. The next plants I want to look at is actually a pair. The post oak and little blue stem. So you all might have heard the term oak savannas, which is sort of basically a grassland with trees sprinkled on it. It's kind of like a park sort of setting. You know, lots of native grasses, and then post oaks and some other trees kind of scattered around. And that's an ecosystem that was around Northwest Arkansas a lot before European settlement and development and everything like that. It was pretty widespread, and it's all over. You know, from Minnesota to Texas and on to the east, it's a really important habitat. And it's a dry habitat. It's kind of a scrubby, tough kind of place for plants to make a living. So these plants are used to drought. They can tolerate that kind of thing. But we don't know, for sure how they'll do with conditions in the future. And so this experiment was actually down in Texas about a decade back, where they basically put these plants through the conditions that we're expecting. Like they delayed the rain from reaching them, and they gave it more all at once, and just to see how they do. And they all made it. They all could endure it. And little blue stem in particular, which has this really lovely rust color in the fall, should be popping up pretty soon actually. Grass in particular can pounce on the rain when it comes. Like, oh my gosh, it's here. It can absorb it really quick. It can put it to use really quickly and grow. But as time goes on, as a tough year kind of drags on and wears it down, that advantage starts to fade. This study found. Its advantage over post oak seedlings starts to dwindle. So you might start getting more trees in this landscape, really a different balance than before. But also, importantly, is that they both kind of start to lose out to cedars, eastern red cedars, which at least in this experiment didn't really give a rip about the rain not being around as much. They just loved it. And if you're familiar with cedars, it is a native species that acts very invasively and can really take over glades and clearings and kind of these open spaces and be places where it shouldn't, where it wouldn't be otherwise, if fire and other natural factors were still in play as much. So we have that to look forward to, I guess. Cedar getting even more of an edge than it already had. Another grass that I wanted to take a look at is big blue stem. This is a really important tall grass prairie species. It gets like 6-8 feet tall, and in tall grass prairie it can be up to 80% of the biomass. So it's just a hugely important ingredient in that sort of ecosystem. And it's very widely distributed, as you can see from that map. It's all over the place, which is a good thing. But again, a fairly recent study found that its core range, like its ideal conditions, could shift to, or are likely to shift to the northwest by even hundreds of miles. And the important thing, I should have said this before, but when we're talking about ranges shifting and moving, that doesn't mean necessarily that all the plants that are out of that range will die. You know, things can kind of concentrate in their ideal conditions, maybe like on a northern slope or a ravine, you know, where things are a little cooler or a little more moist. So it's not that a plant that has to move will just disappear completely, but it could be limited. It could be kind of concentrated in certain spaces, or it could just not thrive as much and struggle a little bit more. And that's what this study found, actually. So here in Northwest Arkansas, in this area, what their models found, what their modeling found, was that little blue stem could be almost lose almost half of its height in terms of adapting to the conditions that we'll have. It could grow 3 or 4 feet instead of 6 or 8 feet. And its leaves would be narrower too. It would look more like the big blue stem that you find out in Colorado or that kind of place, more than what we're used to around here. And this just illustrates that point. So the darker green that you see with the black line, that's that core ideal range that I was talking about. And then the left is kind of the current situation, and we're in that ideal range, you know, just on the very edge of it. The middle is a more optimistic climate change scenario and seeing how things would change with that. And then the right is a more severe climate change scenario. And it's packing up and moving to the Great Lakes, basically. So I wanted to look at milkweeds. I'm sure all of you are familiar with milkweeds. There's a whole wide variety. It seems like every week there's a new milkweed that I've never heard of. And these are prairie species, these are woodland species. A lot of them have a lot of drought tolerance to them. And of course they are essential for monarch butterflies and their caterpillars. And unfortunately, it looks like at least all the species that I looked at, so this is like butterfly weed, common milkweed, swamp milkweed, purple, green or spider milkweed, they look likely to be affected by climate change, all of them, to some degree. For example, common milkweed, which you might see in kind of roadside ditches, it's the big oval leaves and the big purple puffballs of flowers. We can see that its flowering dates have been moving earlier in the year. And what's interesting about that is that, at least in this study, what they found was that it's not that the flowering time is stretching out, it's just moving. So the flowers are popping out earlier, and they're also going away earlier. Which, you know, this is just me kind of speculating about it or talking about it, but that can be kind of alarming when you have something like the monarch, which is on a schedule, you know, kind of on the clock for its migrations, and it needs things to happen when it arrives. And so that sort of mistiming chance starts to pop up. And then another study, this was up in Wisconsin, so you know, not quite applicable to here, or at least a little bit different. But in Wisconsin, they found that common milkweed grows better with higher temperatures. It likes the warmth, but it doesn't like a lack of water, and it starts to struggle with that. And even just within Wisconsin, there was a kind of a north-south gradient where the northern plants could handle these things a little bit better and had a little more in them than the southern plants. And that's just up there. So I can only imagine the difference that it makes for the plants here and how much more they might struggle with the conditions that are on the way. And like I mentioned earlier, you know, butterflies as a whole, but also monarchs, are pretty mobile when it comes to climate change. They can kind of go where they need to go, and where the temperature is where they want it. But in their case, they are constrained by where milkweed can go and where it can move. And again, so that speed of movement and how much it can manage comes into play. So there's you know, beyond what I could read in my research, but there's some chances for kind of the wheels to start coming off, basically, for this whole linkage of the milkweed and the monarchs. And so this is just to give a couple examples. This is common milkweed again, and on the left is kind of the current model for where you are most likely to find it. That's the greens and the blues, where you have the highest probability. And you can see, like if with your mind's eye, Northwest Arkansas is kind of right along that lower red line there, right on the edge of where the plant can do fairly well. And with moderate or severe climate change scenarios, that range is moving away. And what's funny, you can see actually, to touch on this point again, with the more severe scenario, common milkweed does great somewhere else. It'll love it up in Minnesota and North Dakota, but that just means it has a harder time right here. And this is for swamp milkweed, which is kind of the whole same situation. We're right around the kind of the southern end of things, and it's moving several states away under these climate change scenarios. And again, just to stress, that doesn't necessarily mean it disappears entirely, but it starts to have a harder time. I wanted to bring this plant up. This is not a native plant, and I don't think Jennifer's here, but I keep using her picture because it's just such a perfect thing. This is from, I think, the Mount Kessler area. Bush honeysuckle, which you all might know, is an exotic plant. It's from Asia. It was introduced as kind of an ornamental, like nice-looking yard plant, and it has. We gave it an inch, and it's taken several miles. It's really just run loose around the eastern United States. And why this is a problem, or at least one reason it's a problem, is if you look, that little gap there to the right, you can see what's under the bush honeysuckle is darkness. It crowds out saplings and seedlings and other plants, and it catches all the light and it takes it for it. And things like oaks, oak seedlings and other plants, they need that light, and without it, they just won't make it. So these bushes, just standing there, looking all green and lush, are killing this forest here. And so I wanted to look at what climate change would mean for this plant. And at least from the study that I could find, it doesn't love the conditions that are coming. It can struggle with the water stress, just like a lot of other plants would. So it doesn't have like a superpower, at least that I could see, for what's probably on the way. But another thing, I didn't actually know this until I read the study. Another thing that this bush does is release certain chemicals around itself that makes it harder for other plants to grow, to compete with it. This is called allelopathic potential, where it just makes life miserable in its particular area, so that it can just have that space for itself. And with that climate change projection, and with that water stress, that power that it has, that potential to hamper other plants around it, stays about the same, or even becomes more powerful. So it could become an even bigger pain in the neck than it already is. And so just please, everybody, don't plant this plant anymore, and we'll just have to, I guess we'll have to work even harder to remove it where it is. And then on the subject of what you might call invasion or just new plants arriving, this is a native plant too. It's native mostly to kind of the Rockies and this side of the mountains. It's called blue grama. It's a very, very key, important grass species for the shortgrass prairie, which again is adapted to kind of those tougher, drier situations out there. And that shortgrass prairie, the prairie that's adapted to that sort of thing, might kind of come toward us. And you can see from its range, those light green counties, we're right on the eastern edge of that. And so, just to speculate a little bit, we might start seeing this plant. This plant might start kind of making its way in here. And what's interesting about the movement, just a little wrinkle in the movement of plants like that, is that it relies on the peripherals, kind of the fringe communities right along the edge. Those are the ones that move, and they're also kind of weird and wacky compared to like the center of the range where things are really growing well. They can have different traits, different things that are selected to make it in this harder place. And what's interesting about this plant, those peripheral populations can be a little bit more water sensitive. So I don't know, maybe it won't make it over to here. But I just wanted to touch on that possibility of some new things moving in. One aspect of this, it might be out there, but I couldn't find it. Research on kind of the climate change impact on plants that are just native here. Not that they grow here and many other places, but they just grow in the Ozarks and maybe some adjacent areas, but really concentrated around here. So that's like, on the left is the Ozark coneflower, the middle top is the Arkansas blue star, yellow honeysuckle, and then the Ozark witch hazel. And so I don't have like real hard information to give on that, at least as far as I could find. But just to speculate, I am a little worried about these plants, because again, you know, we have a plant's options. If it can't deal with the conditions that are on the way, its options are to move upward and to move sideways. But these are highland plants. These are plants that live in the Ozark Highlands. There's no similar rise like that for several hundred miles around us, and obviously you can only go up so far. Eventually you run out of room, and so I don't know what'll happen. I know I'll be heartbroken if something bad happens, and so that's a point I just wanted to raise with this whole discussion. And so just to give a real brief spiel, this isn't mostly about me, but with all of this in mind, Ozark Roots is the native plant business that I've begun to start. Really, I'm just at the stage of, in the spring, I planted a whole bunch of native plants in my yard and agreeable friends' yards, and that's kind of my farm. That's my seed source. And so I've been collecting all those seeds this fall as much as I can, and I'm hoping to start selling plants in the spring, just so you know. But the focus of this is, like I said earlier, plants that are native to the Ozarks specifically, and with an emphasis on, or a focus on, plants that have adaptations that could be helpful for what's on the way. So like drought tolerance and things like that. For example, just to give a couple example species, on the left is called eastern gamma grass, which is a kind of a riparian sort of species, you know, along rivers and streams. So it has a flood tolerance to it, you know, an erosion control aspect to it, but it is also drought tolerant, at least to a degree. So it's kind of, and that combination of flood tolerance and drought tolerance seems ideal for what we've been talking about, you know, longer stretches without rain, but also heavier rain when it comes. So I really like plants that have that combo. The middle is Maximilian sunflowers, which is just an enormous, beautiful prairie species. Like a lot of prairie species, it has deep roots and drought tolerance to some degree. And then the one on the right is called spice bush, which has a really lovely smell when you break the leaves, and is important for the spice bush swallowtail butterfly, of course. And that's a nice kind of more woodland species that can take some shade and can take some flooding, but can also take some drought. The important part of this is, or what I wanted to raise also is, you know, putting together this presentation and reading all this research and thinking about this more, I've realized that it's a learning experience for me too. You know, I had been thinking of it in sort of a simple, kind of straightforward way, like plants that have drought tolerance, like that'll be great. You know, because they can make it through those long stretches. But as we can see, even plants that have some drought tolerance could be kind of shifting away. So it's a continual process for me, I guess. I just wanted to admit that I'm going to keep learning about it. You know, it's sort of heresy to say that we might want, you know, genetics from other parts of the country. We might want to start kind of getting seed from Oklahoma or Texas or Colorado. You know, generally you want local genetics. You want the plants that grew up here and lived here. But things are changing, and so I don't know for sure. I'm not like advocating for that really, but it's something that we have to start thinking about, I think. So this is just a continual learning process for me. But I'm going to do as best as I can. You know, it's with this issue in general. Other people have said this, that, you know, you can't wait till you know everything. Like we have to just kind of get moving and do what we can and learn on the way, because it's just so urgent and it's happening right now. So anyway, that's what I'll be doing. And so like I said, I'll be preparing for having plants in the spring. This QR code is just to a really simple Google form to sign up for my newsletter, where I'm doing to just kind of keep in touch, since I'm not really selling anything, just to give updates on my progress and let you know when the sales actually start and everything. So if you are interested, no pressure, you can use this. There's also a notepad in the back if you just want to use pen and paper. But I'd love to stay in touch with you all and keep you abreast of what's happening. In the meantime, there are plenty of local native plant growers that are already up and rolling and selling plants, even right now as we speak. And so I want to share all this information with you too. All of these should be on Facebook, so you can find them there. But this is their other contact information. Peel Compton does spring and fall sales. Its fall sale is actually going on right now and continues through Saturday. That's just up in Bentonville, so you might give them a visit. Bluestem Hollow was just started by Nate Weston, whose name you might know. He's kind of a titan in native plants around here. He's just over in Lincoln, and he's been selling at farmers markets and other events like that. So you might give him a look. The Master Naturalists, which I joined this year, I think it's just a spring sale that they do. Yeah, so they'll sell a bunch of native plants in the spring, like at the Botanical Garden and other places. And I feel that, I don't know, I don't hope Rose isn't here. They might have more contact information, but you can at least use that email address. Moonlit Heights is just over in Huntsville, really great little operation. Again, they're mostly at farmers markets and similar events, but they'll also sell directly. And then up in Missouri, Ozark Soul is kind of a traveling seller of native plants. They come to Fayetteville sometimes, or Eureka Springs. I think they have one just coming up in Eureka Springs, so give them a look as well. And then I just wanted to end on what might be kind of a cheesy note, but this is a picture I've always been proud of. I took it several years ago in Springdale, just off of the Greenway. And these are tick-seed sunflowers, or beggar ticks, I think is the name. Just growing wild in this, paved over concrete drainage ditch. Kind of the most inhospitable place that I could think of for a plant, and just going crazy. And it just sort of illustrates, this isn't strictly climate related, but, I care a lot about environmental issues, and I pay a lot of attention to the news, and it can be very depressing, a source of a lot of anxiety. And plants are a source of hope for me. And I always get emotional when I talk about it. But plants, they can't solve all these problems. They can't solve climate change on their own. They can't solve pollution. They can't solve invasive species. They can't solve all the different ways that we are damaging the world around us. But what they can do is help with all of those things. They can help with all of them. They absorb carbon in their roots. Their roots hold on to soil. Their roots absorb pollution. They support pollinators and other bugs and insects. They support birds. They just do everything. They do 1,000 things that we depend on. If we let them, sorry, and with climate change and this kind of perspective to it all, it's not just if we let them, but if we help them. If we help them. I'm sorry, it's this good grief. Anyway. And so I hope to help that happen. I hope you all do the same as much as you can. So anyway, that's it. Thanks again for coming. And I've talked for longer than I ever meant to, but I can try to answer a couple questions if you like. It's up to you. Yeah, go ahead.
We have a lot of bush honeysuckle around the Markham Hill area, and I keep wondering, we get it together to get rid of it. What are good things to plant understory back?
Yeah, well, there's a lot of really great shrubs that can deal with complete shade or just partial shade. Spice bush was one of them. Ozark witch hazel is a really lovely one. That's the one that has really wacky little flowers in the middle of winter. Oh gosh, I'm trying to think. There's a few more, but there are options. There's also a native. I just learned this a couple months ago that there's a native burning bush. It's called the wahoo or eastern wahoo, which is a funny name. But it turns bright red in the fall and has really interesting red little fruits on it. So that it's actually kind of similar in appearance to bush honeysuckle and the invasive burning bush. So there's several to pick from, definitely. Yeah. Any other questions? Yeah, go ahead.
Do you have enough space now for what you're doing? Or are you looking for extra space for planning experience?
Yeah, and I'm sorry. I should have repeated the earlier question. But to repeat that, you're asking me if I have enough space to get rolling, and the answer for now is yes. I have enough to kind of get started. Actually, one of the watershed partnerships. It's not set in stone. It hasn't been signed to or yet, but they might offer me kind of a stretch of lawn, essentially, enough space for a greenhouse and some tables and things like that. So that's really, really very generous of them, and that should be enough for me to get started because it's just me. And then there's other people who have expressed kind of some willingness to help out in that respect, and so it could grow from there. But also I'll hear anybody who's willing.
I have neighbors who have 144 acres set aside in perpetuity in forested and, just the kind of hills in the land out here. I don't know, they're both professors at the university. And if you wanted to have some actual wild land, to work with,
Yeah.
I don't know if they would do it, but I bet you.
Well, sure, and so you were talking about someone who has scores and scores of acres who might be willing to help out. And really, kind of what I think you're touching on too is even besides just letting me kind of set up an operation, even just letting me walk around and pick up seeds would be really helpful. So I'll absolutely.
It's an unpolluted area.
Yeah, sounds nice. Any other question? Okay, well, thanks again, everybody, for coming out. I sure appreciate your time. I hope it was interesting and informative. Thank you very much.